Hello students, we are going to take the discussion of the Chemistry Olympiad, that is Indian Olympiad Qualifier exam. We'll be having paper 1 first. This is question paper code number 31 what we have. First we'll be taking the discussion of the objective questions followed by the subjective ones later. And we are going for organic questions first. This is going to be section A1 where single option correct questions are there. The very first question is about the polarity of the solvents. Here we have been given some solvents and we have been asked which of these solvents are, basically the set has been given and we have to choose the set in which all the solvents are polar. How will we doing this thing is, first of all you need to understand how this polarity is being compared. We understand already how this polarity is supposed to be compared. The dipole moment basically depends upon certain factors. The first thing is difference of the electronegativity. If we have got two elements X and Y bonded, greater the difference of electronegativity, we can expect greater will be the polarity. First thing. Second thing is if you have got some two elements, they have got same difference of electronegativities, then bond length comes into picture. If you remember, the dipole moment mu used to be Q times D. So delta En, which was deciding Q, is one factor. Bond length D is another factor. Both these factors must be taken into consideration to finally decide which compound is having greater dipole moment. Also, when we have got more than one bonds present, say we have got some compound like EX3 or EX4, something like that, then we have to do the vector addition of these different dipole moments. So using these 2-3 things, we should be in position to decide which compound will be having polarity, which compound will be having no polarity, or which will be non-polar. So here are the structures of all these compounds. The options which we have been given, this was P, Q, R, S, T. Only one compound over here we are seeing is non-polar. When we are having mu equal to 0, we mean to say these compounds are non-polar. Rest all compounds where mu is non-zero, you can see these compounds are considered to be polar. So basically we are going to do the vector addition. Here the vector addition of this Br bond and this carbon Br bond is going to be oriented in like this direction. Here oxygen will be having one lone pair, another lone pair. So the resultant vector for all these bonds, the 1, 2, 3, 4, resultant vector is going to be somewhat like that. In nitrogen also, if we are keeping a lone pair somewhere here, then this vector is going to be oriented like that. Addition of all the vectors also, if you are doing, then the addition of this vector, if you do that, basically this should be like that. That is also going to be somewhat the direction. In carbon fluorine bond in this trans compound, these two vectors are going to be cancelled out completely. That's why this is going to be non-polar. This option number S was a little bit tricky because if sometimes students find this to be written like this is hydrogen here, this is one hydrogen here, hydrogen goes below the plane, hydrogen comes above the plane, then it appears that all these dipole moments are going to cancel out. That's actually not the case. If you see here, what we have done is we have highlighted this with the star mark. This compound is having some possibility of conformational isomers to be existing. For conformational isomers, when there was a mixture present, what we have learned, in the cases of mixtures, the formula for the dipole moment for the mixture of conformers used to be sigma xi. Xi is the mole fraction of all components multiplied by their dipole moments. So see what is happening in this case. We have got this compound existing in two conformers. One is anti, one is gauche. Quite contrary to what a number of students might be thinking, in comparison to this, the other form, the gauche form, is more stable. And the reason comes from some hyperconjugative stabilization, which we have been sometimes calling as the gauche effect. So this form number A, this form number B, This is having dipole moment non-zero. This is having dipole moment mu is equal to 0. Here we should say mu was non-zero. Whenever we are having such a situation, the theta of the mixture, the dipole moment of the mixture is going to be always non-zero. So only option number R was there, which was not polar. All other were polar, the cases of the polar thing. So our correct option was the first option, in which P or S were given as the options. That was question number 1. Going to question number 2. We have been given here this one compound where we have to synthesize. This is basically some bicyclic compound having 2 ketonic group and 1 unsaturation. We were asked how this compound could possibly be synthesized. We call this compound as Wieland-Mischel ketone, and we have been given some of these options. Pair of compounds have been given. Using these compounds, we were asked which of these compounds can be giving you this particular compound as a base catalyzed reaction is there, and these two compounds are reacting, we are getting this. Okay, we'll see how the answer to this question is coming as B. What we need to understand here in this case, there is an aldol condensation reaction. Conjugate addition is going to take place, and after that there is one step what we are understanding as the intramolecular simple aldol condensation is going to take place. So this is in the first step, the carbonyl present over here on this dicarbonyl compound is attacking onto this conjugated ketone. This kind of product is being formed in 2 steps. Step number 1 is soft base attacking the soft acid, followed by generation of this enol, which is converting into the keto form. And there is something what we call as HSAV principle. We'll be seeing that soft base preferably will be attacking the soft acids. Then this compound what is being formed is further attacking, and in the second step, which we are calling as base catalyzed condensation, once again we are getting this compound, and then this is the intramolecular aldol reaction, and that step is elimination of water to give you alpha beta unsaturated carbonyl compound. This is alpha beta unsaturated carbonyl compound is being formed. And in the previous case, here there was a new carbon-carbon bond formation taking place. Here, this is the new carbon-carbon bond formation taking place here. So this is how this compound is being synthesized. We'll have a little bit detailed discussion about this, how these steps are taking place and what are the reasoning behind that. So the very first step was when we have got this dicarbonyl compound, sodium hydroxide is reacting. This hydrogen is very much acidic hydrogen. This hydrogen is going to be taken by this base. This carbonyl what is being generated, we call this as a soft base. The reason is very much simple, because this negative charge what is present on carbon can be delocalized onto this oxygen atoms. Oxygens are very good in stabilizing this negative charge, so we can write this resonating structure as this will be one resonating structure. Another resonating structure, the negative charge can be going onto the another oxygen onto the other side. Let this be double bond O, and this negative charge goes out here. Negative charge stabilized by 2 carbonyl groups is going to be very much stable thing, and we are saying this soft because this carbon is going to have relatively less charge density in comparison to a usual carbonyl, where this carbon is bearing the full negative charge itself. So this is the soft base. Now think about the HSAV principle. The principle is saying us, this principle tells that whenever we have got a soft base, this will preferably attack the soft acid only. So this is our attacking reagent what we have generated. Where this is going to attack, we need to see there was one conjugated compound. In that conjugated compound, there are 2 ends we can see. One end over here, this carbon, which we are considering as soft because this is a carbon-carbon double bond, relatively less polarization will be present here in this bond. Another one, this is carbon-oxygen double bond. This carbon is going to be a quite higher magnitude of delta positive charge because of the polarity of this carbon-oxygen bond, and also there is a pi bond present. So greater magnitude of charge will be classifying this particular carbon as the hard acid. And as we understand in HSAV principle, If this is a soft acid, soft base being generated over here, this will preferably be attacking the soft acid itself. So attack onto this particular carbon is going to be preferred. Let us see. That was the carbonate, soft base we'll say, and that is our conjugate carbonyl compound. Soft reaction is going to take place. There is a formation of when this is happening, there will be this bond will be shifting, and then there will be another bond shifting. The carbon oxygen pi bond will be shifted towards oxygen like that, and then we will be having the new carbon-carbon bond formation taking place. We can see here is the new carbon-carbon bond formation taking place. I can highlight that bond. This is the new carbon-carbon bond formation, what is taking place, and we'll see here as a result of that carbon-carbon bond shifting, you'll be getting here basically the negative charge first, which will be taking 1 H plus from the solvent. This kind of enol form will be generated, and we understand this enol form will be in equilibrium, in tautomeric equilibrium, we should say. This will tautomerize into the ketonic form. So this is the very first step when this conjugate addition is going to take place. The second step over here is going to be another step, which is intramolecular aldol reaction. This is our compound which has been generated in the very first step. Now we have got sodium hydroxide, and there is one acidic hydrogen present over here. So this hydroxide will be taking away this acidic hydrogen. Negative charge will be present onto this alpha carbon of carbonyl group. That gives us what we can call as enol or enolate. Basically, this is going to be resonance stabilized by the negative charge of oxygen. So we can write that as double bond, negative charge goes onto oxygen. This is going to be basically greater resonance contributor. Anyways, this carbon is going to be the nucleophile, which is going to be basically the attacking reagent, this carbon. And this carbon can be attacking onto this carbonyl group, or it can be attacking the another carbonyl group if it would have been written the other way around. Like if we would have written this whole thing onto that side here, then we could have attacked onto that particular carbon. It hardly makes a difference. Both are going to be exactly same unless and until we have got any other group present on any other positions in this particular ring. So if you have got one methyl group here or one ethyl group here, then it could have made a difference. Here they are essentially the same. Now here as the attack of this carbonyl, the carbonyl onto this carbonyl group, we are going to have this intramolecular aldol reaction taking place. So here there is a new carbon-carbon bond formation taking place like this. And as a result of this new carbon-carbon bond formation taking place, here we are having now another 6-membered ring formation possible. So this new 6-membered ring formation is going to give us, this is what we are calling as beta hydroxy carbonyl compound. This is going to be beta hydroxy because this is carbonyl group, reference carbonyl group. This is the alpha carbon, this is the beta carbon. Beta hydroxy carbonyl compound is being formed. And we understand in presence of base and heat, this is going to be one case of even CV elimination. Where first of all this hydrogen is being taken, the negative ion carbon ion is being generated, in the later step OH minus ion is being lost, and that is how this alpha beta unsaturated carbonyl compound is generated. There is a generation of a double bond over there. This double bond is being formed onto that position. That is how this Wieland Michel ketone is being generated. So that was the option where we have started with this 1,3-dicarbonyl compound and one conjugated ketone, which gave us this compound. A little lengthy discussion we have had to help understand how this conjugate addition is taking place, and followed by how this intramolecular aldol is going to take place. That was question number 2. Moving on to next question, question number 3. Here we are given some compound and we have been asked what is going to be the possible product. So how we are going to judge what is going to happen. See, we understand this is going to be the case where we have been using one compound which is formaldehyde. We are also using some base, and there is one aldehyde group already present. If aldehyde group has got the alpha carbon present, like this, here we are having, we think about the possibility of the Aldol reaction. Also, we see some formaldehyde coming over there. There can be some possibility of Cannizzaro as well. So, the correct answer for this is going to be the option number A. And how we are proceeding. So, because there is enolizable hydrogen present in the very first compound, 2-methylpropanol, we see a possibility of crossed aldol condensation, because this carbon, this hydrogen, when this is being lost to the base, we get a carbanion over here. That carbanion can generate on this HCHO. That is what we are saying. This first step is going to be the crossed aldol condensation. But once that reaction has happened, the intermediate being formed, there was just one alpha hydrogen which we have just shown here. After that step, alpha hydrogen will no longer be available. Then we have a possibility of the crossed Cannizzaro reaction. So this compound, after reacting with HCHO, say converts into some compound number Y, first one, and then this Y will be undergoing, the first step is going to be our crossed aldol. Y upon reaction with further HCHO, because we can see they have given us this in excess, we can think from there that HCHO might be reacting more than one times. So that is going to be the cross Cannizzaro, and then we'll be getting some final product. And in that cross Cannizzaro, we understand that the more reactive aldehyde was supposed to be undergoing attack of OH minus ion, and that was converting into hydride donor, and that was converting into the corresponding carboxylic acid. So see how these steps are taking place. The very first step is HCHO. This is basically how this product is being formed. The very first step over here is going to be this calcium hydroxide is going to abstract this hydrogen which was present over here in the previous step. So we are getting the carbanion. This carbanion, we understand, is essentially part of enolate and carbanion equilibrium, that resonance hybrid. And then this carbanion can be attacking onto this formaldehyde. This bond will be moved to oxygen, and we will be getting this kind of CH2OH being generated. This part is coming from the formaldehyde. O minus will be taking a proton from the water. This very first step we are calling as crossed aldol condensation. The new carbon-carbon bond formation, what is taking place over here? See, we are emphasizing this new carbon-carbon bond formation in all the reactions because that has got very much synthetic utility, and you could be seeing this as we have tested a number of times how this new compounds can be generated, how new carbon-carbon bonds can be generated. That can be giving us enormous possibility of getting variety of new compounds being synthesized. Okay. That was the first step where we have now got this compound we called as Y earlier. Now this compound number Y does not have any alpha hydrogen present. There is one methyl group and one hydroxymethyl group present. Now this has a possibility of undergoing Cannizzaro. So in cross Cannizzaro reaction, now we have got two aldehydes. One is this aldehyde, what we have just now generated as aldehyde number Y. Another one was the formaldehyde. We understand which of these two is relatively more reactive, because here there is hydrogen only, here there is some alkyl group present. So this is going to be more reactive, more delta positive charges present on that carbonyl carbon. So our hydroxide ion is going to attack on this formaldehyde. Then we'll be getting this intermediate generated, which is going to behave as hydride donor. And we understand when we have got one hydride donor, this is going to lose one H plus. Basically, this is going to transfer one H plus to another aldehyde, and when that is happening, this oxygen lone pair will be coming in. We will be getting this thing converted into OH. And okay, so this compound, the compound number Y which we have taken, is converting into some alcohol, and that hydride transfer what had taken place, this is converted that compound into alcohol. basically this is the anion of the alcohol, conjugate base we can possibly say, and that is the acid. We understand beyond this point what is going to happen. This acidic hydrogen from the formic acid is going to be moving on to this acidic hydrogen from here will be moving on to this oxygen, so that will be converting into alcohol and this will be converting into formate ion. That was the question based on the Aldol and Cannizzaro, both the reactions put together. So the final product which we are getting is, this is going to be, we can do the numbering of this compound. So this is going to be, we'll be starting our numbering from whichever side. This is going to be basically same thing. So this is carbon number 1, carbon number 2, carbon number 3, and two methyl groups present over there. That's going to be 2,2-dimethyl propane 1,3-diol. That's going to be our final answer. Okay, moving on to the question number 4. In this question, we are given some hydroxyaldehyde, and we are in this hydroxyaldehyde, we are reacting this compound with the acidic medium first, and then we are taking excess of methyl alcohol in presence of CH3, in presence of acidic medium basically. And for the second step, they are saying we need to heat it for 12 hours. Then we are getting some compound number P. We are being asked what this compound number P can possibly be. So we'll be ultimately getting here the compound number C. And the strategy what we should be following, the concept what we could possibly be using is, the first thing is we have got intramolecular reactions which are going to be much more favored in comparison to intermolecular reactions in variety of places. We might have seen that already. Second thing is, when hemiacetal are being formed, they are reversible in acidic medium as well as in the basic medium. They can be reverting back into the starting compound. But if this is a cyclization reaction, then this hemiacetal formation can be moved in the forward direction. Hemiacetal can be stabilized. So when we are saying hemiacetal formation is reversible, but this hemiacetal formation can be shifted into the forward direction, this thing, if cyclic hemiacetals are formed. Okay, and the third point is, acetals which are being formed, they can be quite stable and they can be existing in the given solutions. In fact, in basic medium, acetals are not decomposing, they are stable, and in acidic medium also they can be stable up to a certain extent, but they are converting back into the hemiacetals very easily or converting back into the nodal compounds very easily. So in this case, methyl alcohol being taken in large excess is to drive the second equilibrium of our hemiacetal to acetal. We have taken hemiacetal and we have taken CH3OH in excess. We want to drive this equilibrium into forward direction to get converted this into acetal. And you can see here we need to require heat and we need to wait for a pretty long time to get the good enough concentration of this compound what is being formed. Let us see how this reaction is taking place. So the very first step is the cyclization reaction, where the oxygen from here can be, alcoholic oxygen basically can be attacking, and this carbonyl group is actually being activated. This carbonyl group, when this is attacking the H plus from the solvent, this converts into the protonated aldehyde. This is, you can say, activated carbonyl compound in presence of acid. This activated carbonyl can be attacked very easily by this alcohol. So we are getting here a 5-membered formation taking place, which is basically an acetal. And because this is the hemiacetal which is cyclic, this equilibrium we can see is going to be favored, and this is going to be moving in the forward direction. The second step, this hemiacetal this OH group is basically being protonated. This is converting into good giving group. And now methyl alcohol, what we have taken in large excess, is going to drive this equilibrium again in the very much forward direction. If you are not taking this alcohol in excess, this reaction can be going in the backward direction. This is going to be reversible. So that is how this acetal can be generated, and we can be getting this final product formation possible. To generate acetal, basically we have adopted all that technique to get it going in the forward direction. The next question we are going to take is on amine, and we are being asked about the Hinsberg test. We have got the options in which there are mixture of amines. Like in some options there is 1 degree as well as 3 degree amine, 1 degree as well as 2 degree amines, or 2 degree and 3 degree. Those kind of cases we have been given. So we have to be little bit careful about choosing our options. And here we have been given that when this compound, this amine basically is being reacted, that's compound number X. When this is being reacted, this is producing a solid compound Y, meaning that this is going to have less solubility. This could possibly be forming a precipitate. Then this precipitate, what is being formed, or this compound Y, what is being formed, this is insoluble in 10% aqueous NaOH. This compound is being insoluble in basic medium. That could be giving us an idea that this compound might not have any acidic nature present. But later on, it is being told that Y compound is dissolving in 10% aqueous acid. That gives us some idea that this compound, what is being precipitated as Y, that may be having still some basic nature, and that's why this is being soluble in the sulfuric acid. So we have to identify X of the given options. Here we have got the very first compound where we have got the 1 degree nitrogen present, and this side we have got 3 degree nitrogen present. Here we have got this side, this is 3 degree nitrogen present, and on the right hand side there is 2 degree nitrogen present, 2 degree amine we should say. Here we have got 1 degree amine, and the same molecule there is 1 degree amine, another one. Here we have got this nitrogen which is 3 degree, and on the other side we have got another nitrogen, this one, which is again 3 degree. So we have the options where 1 degree, 3 degree are present, 1 degree, 1 degree, 3 degree, 3 degree, and 2 degree, 3 degree. These kind of options we are having. We have to choose our option. The answer turns out to be B, and we will see why B. Why not the other options? Why not D, for example, C? And this question is actually students and teachers might be taking it in a very light way. This is not that much straightforward. The purpose of this question being asked was something deeper, which mostly students or people could not see it correctly. We'll have a discussion. Let's have a look. So first of all, this Hinsberg reagent is supposed to be reacting with the amines 1 degree and 2 degree to form sulfonamide. There is one disclaimer. Most of the textbooks what we go through, they teach us that only 1 degree and 2 degree amines react. 3 degree amines do not react at all. That's actually not true. We'll see in a moment, and we'll be citing some references, people who have done things in the lab who have reported their results. We'll be talking about that. Okay, so 1 degree amines, when they're reacting, they are giving us some precipitates, and these compounds which are being formed, they are soluble in bases because they can still have an acidic hydrogen, and then they are becoming further insoluble in acids because in acidic medium they cannot be converting into ionic forms and they can be remaining HH. One very much good idea about the solubility of the organic compounds is if they have got acidic nature, they should be soluble in bases like NaOH, and if they are having basic nature, they should be soluble in acidic things like HCl or dilute sulfuric acid. That is very much clear. Okay, now if you take secondary sulfonamide, that's which are coming from the 2 degree amines, because there are no acidic hydrogens left, both the just one hydrogen was present, which is being lost as HCl when Hinsberg reagent is reacting. We'll be seeing that reaction sequence in a moment. So now this is having insolubility in bases, and because the nitrogen's lone pair is also not very much basic left because of its resonance, so this is again remaining insoluble. So what is the thing which will remain soluble in the acid? The one where nitrogen's lone pair is still remaining intact. How is that possible? That can be happening with the 3-degree amines. The reason is when 3-degree amines are reacted, then the reaction is actually not going very much in the forward direction. Most of the times, the 3-degree amines are only present in the reaction medium. There is basically one equilibrium. That equilibrium is not going in the forward direction unless and until we have got some very good reasons or we are waiting for sufficiently long enough time to get the significant amount of the product being formed. Then we are thinking this is becoming dissolved in acid. Why this is dissolving in acid? The nitrogen, which is basic, now if there is not enough sulfonamide being formed, or it tends to get converted back into the 3-degree amine, that is pretty much basic, and that should be dissolving in the acid. Okay, now see this solubility pattern. There is some confusion in the solubility pattern over here. We can refer to this reference where we have seen the solubility patterns, and there is this sequence of separation of amines reported in the same reference. That book has detection and identification of the organic compound. This book we can refer to see the things what we have been saying. 1-degree amines are going into the alkaline aqueous layer because that salt which is being formed will be soluble in this basic medium, or basically in aqueous medium. In ethereal layer, when we are reacting, and basically we are reacting our mixture of amines with Hinsberg reagent, and then we are putting sodium hydroxide, and at 60 degrees Celsius we are waiting it for some time, and then this is being extracted with the ether. So when we are extracting this with ether, then upon extraction we are getting the ethereal layer, and this ethereal layer there are 3-degree amines as well as 2-degree amines present. And now to separate these 2-degree and 3-degree amines from the ethereal layer, what we are doing, once again, we are putting HCl. In this HCl, that's hydrochloric acid, we are trying to separate. And if you see here, what is happening in the aqueous layer, like what is the thing what is going in aqueous layer, that is acidic or aqueous layer we could have said, and what is remaining in the ethereal layer. So in the aqueous layer, because HCl is going to dissolve the basic amine, that's 3-degree amine, this is passing on to that, and the secondary sulfonamide, which is not soluble in acid over here, this was not soluble in the base over here what we had taken, so this was not going into the aqueous layer. That is how 2-degree amine is not soluble in acid, and emphasizing over here not soluble in acid and not soluble in bases as well. So this passes into ethereal layer. The subsequent methods that we have used are just for the purification and separation, how they are recrystallized so that we can get the pure forms. This thing is reported in this paper. In this book, we can refer to that if we want to verify. Okay, moving on, these are the reactions what are happening. We might have seen these reactions when we learned the amines. So nitrogen is attacking onto sulfonyl chloride and we are getting the sulfonamide. The sulfonamides are forming precipitate. They usually are insoluble in the given medium where this reaction is taking place, but they can be made soluble if we are having excess of the sodium hydroxide, because that hydrogen is basically acidic in nature, and that acidic hydrogen which is there, this acidic hydrogen what we have mentioned over here, this acidic hydrogen which is here, this can be basically undergoing tautomerization and can be reaching over there. Most of the times we can be finding this thing written as this way. The nitrogen is containing hydrogen, but this can be going on to the oxygen as well, just like we might have seen in the normal amides. This is sulfonamide. So this hydrogen anyhow is going to be acidic, and that's going to take sodium hydroxide, loss of water, and this is going to be the salt formation taking place. And we understand whenever there are the salt formation taking place, things can be made pretty much soluble in the aqueous medium in majority of the cases, at least for the organic compounds that we understand. And this compound is not going to be soluble in acidic medium, because if we put acid into it, this compound, if you are putting basically acid into this compound will be converting into that SO2 and NHR. This compound is not being ionic in nature. This will not be made soluble because that phenyl ring and alkyl ring, they'll be having too much of the hydrophobic nature, and that cannot be overcome by the these attractive forces of the water molecule. That remains insoluble in acidic medium. 1 degree amine. 2 degree amines, if you see, here there was only one hydrogen present, and that is also being lost as HCl when this reaction is taking place, and sodium hydroxide's presence in this reaction medium can be helping this HCl to be removed easily, and this reaction can be made to go in the forward direction. This compound again forms a precipitate. And now, because this nitrogen is not having any acidic hydrogen left, this compound is not going to react with this NaOH, sodium hydroxide. Also, lone pair of nitrogen being in resonance, this is not even reacting with HCl. So this is not reacting with sodium hydroxide, this is not reacting with HCl, nothing is happening. But the sulfonamide, what is being formed? The sulfonamide is having its insolubility in the acidic as well as basic medium. That is what we want to emphasize here. In our given question, the thing was the amine which was given, it is soluble in NaOH, alkali, and insoluble in acid, that's H2SO4. So possibly 2 degree amine should not be the reason. We should not say straightforward that the 2 degree amines are going to be the answer, because that is insoluble in sodium hydroxide. And coming to 3 degree amines, this is the thing we see that this reaction is taking place. Equilibrium may not be going very much in the forward direction, but this does take place up to a certain extent. And here we are getting the compound which is going to be having a kind of ionic nature. But this compound, when we are trying to dissolve in the medium, this compound is not going to dissolve in basic medium, because this equilibrium is not lying in the forward direction. The mainly thing what is present in our product mixture is 3 degree amine. This is the main constituent present in our reaction medium. So if 3 degree amines are the main constituents in reaction medium, then when we are talking about solubility, these should be soluble in what? These will be soluble in acidic medium, because in acidic medium the 3 degree amine will be converting into R3NH plus OH. That's 3 degree ammonium hydroxide. These compounds basically that's converting into some base, and that aqueous base it is converting into, and this is being made soluble in this aqueous medium. Now, coming back to, now we are comparing the solubility patterns, and we are seeing here how 1 degree, 2 degree, and 3 degree amines would be reacting. And basically, this same compound having more than one kind of amines, if they are reacted, then what kind of pattern we are going to see in the final products. This was the case for the option number A, option number B, option number C, and option number D. So here, the compound which was given to us when these different compounds are reacting, basically we can analyze on the basis of the information we have talked about in previous section, previous slides. These three compounds are going to precipitate with Hinsberg reagent. The last one is not going to precipitate because there is very small amount of reaction taking place. No significant sulfonamides are being formed which could have possibly precipitated. So no such thing is happening. 1 degree and 2 degree things are getting precipitated with this Hinsberg reagent. Here we have the cases like 1 degree over here, 2 degree over here, 1 degree, 1 degree, these will be precipitated. And talking about solubility, so when we have got 1 degree amines, like this is having 1 degree, this is having 1 degree, these are going to be soluble in the sodium hydroxide. Here we have got this thing which is 2 degree amine, and this is which is got 1 degree amine. So because this is 3 degree amine. Because of presence of 2 degree and 3 degree amines, here solubility is not going to be present in sodium hydroxide, and that is what we have been looking. So this is 2 degree amine, but what about the presence of 3 degree amine? This presence of 3 degree amine over here will make this thing to be soluble in HCl as well. That is the thing what is most important in this question, what we cannot overlook. Okay, So what we can finally say, this compound was X, this compound was Y, which was forming the precipitate. Now what this compound Y would be, what is forming precipitate? If we are assuming this reaction of 3-degree amine is taking place up to very little extent, then this thing is going to be present as the compound number Y, what was forming precipitate. And this tells us that why the presence of this nitrogen's lone pair onto the delocalization of this SO2 will not be making it enough acidic or not enough basic basically, but this nitrogen's lone pair is not going anywhere, so that is going to make it soluble in sodium hydroxide. So solubility in sodium hydroxide is coming because of this nitrogen atom from the starting amine, and insolubility in the sodium hydroxide is coming because of both, because this is basic, cannot dissolve in sodium hydroxide. Here nitrogen's lone pair is although present, but this is going to be delocalization. There is no such hydrogen present on this nitrogen, that's why this is not happening. And if we believe up to certain extent reaction is going in the forward direction, then this could have been the product, and then because this is not in significant amount, this will be the first thing is going to be the major thing which will be present, and that's why we are seeing these kind of observations. Now we'll be seeing what is compound number like what is happening to Y in the sodium hydroxide. There's no change happening because there's no acidic hydrogen available. And then when we are putting this in HCl, then what is going to happen is this NHMe, what we had seen here, this part is going to interact with this water molecule, and this is going to produce into this thing. Whatever that the benzene sulfonyl chloride would have been present, that would have been converting into this thing. We can also let this can be coming from this compound as well. Mainly we'll think this is coming from this. That's how compound number X was 1, where 2-degree amines as well as 3-degree amines were present. We should not jump to the answer directly on the basis of the 2-degree. Okay, I hope that's clear, crystal clear explanation. Now moving on, we have got one thing left which we should also be very much aware of, what most of our textbooks are telling us, that benzene sulfonyl chloride, that is Hinsberg reagent, does not react with tertiary amine. This is the thing what most of our textbooks are telling, but an article published in this Journal of Chemical Education suggests that if we go deep down, the people who are doing the chemistry in the laboratories and analyzing the results, they tell us that that has happened, that is not the truth, that 3-degree amines do not react at all. And this is what the reference we just talked about in our previous slide, that which is saying the Journal of Chemical Education, that article. It tells us that what is happening in this same reference when we have the 3-degree amines reacting with Hinsberg reagent, this kind of compound, what is being formed, its presence, the evidence that this kind of compound is being actually formed, that comes from the observations. That two reactions are there which are taking place. One reaction is that if you have got excess of the 3-degree amines which is present in this reaction medium, although this reaction is very slow, but if you wait for long enough time, you can get these products possible. This product as well as these products are formed. So we are basically getting secondary sulfonamide and 4-degree ammonium halide. That is the thing what we are getting as the final product after a long time, when we are allowing this reaction to be taking place in presence of excess of 3-degree amine being present. And how that reaction would actually be taking place, we can think from this reaction mechanism. We understand that this 3-degree amine is having nitrogen's lone pair present. This nitrogen's lone pair can be attacking onto this methyl group, and this carbon and this nitrogen bond can be polarized towards nitrogen, because SO2 can be pulling electron further, and this nitrogen was already positive. This may be too much electronegative to pull electron from the carbon, and basically here this whole thing we should consider as the leaving group. This whole thing is the leaving group. So this methyl group is being attacked by this kind of a nucleophile, and this whole thing is leaving. This is the group what has leaved. We can consider this as the leaving group in that case, because nitrogen was earlier positive. If it is leaving, there will be no charge left. Nitrogen will be just gaining one lone pair from the breaking of the carbon-nitrogen bond. And when this nitrogen has attacked onto this methyl, this nitrogen is now getting 4 methyl groups, and then there is a chloride component. That's how 4-degree tetramethyl ammonium chloride is being formed. If you have difficulty understanding this reaction, you can recall the reaction we have done in the preparation of ethers, where alcohols were reacting with the methyl sulfate, and that methyl sulfate was being converted into this methyl ethers, and methyl hydrogen sulfate was formed as one of the products. Okay, now the another observation what this article tells us, that if you have any typical nucleophile which is attacking onto this product of the 3-degree amines with the benzene sulfonyl chloride Hinsberg reagent, then this reaction is quite fast. You need to have relatively stronger nucleophile, good nucleophile we should say. If you have good nucleophile, then this reaction is quite fast, relatively faster, and then this trimethylamine can also be one of the leaving group. We can see here in this mechanism. So this time, this whole thing can also be a leaving group. So depending upon the nature of reactions, basically, we can have our leaving groups possibly changed. Now, this is the leaving group. If you have got good enough nucleophiles available, those good enough nucleophiles can make these reactions also possible. The sulfur can be attacked, and that nucleophile is now attaching over here, and this 3-degree amine is being lost as the leaving group, and chloride is going off in the solution. We have got total 1 net negative charge in the reactants. We have got total 1 net negative charge in the products as Cl-. So that was all about this question on the amines based on Hinsberg's test. The next question we are having is about the peptide bond, peptide linkage, and the number of chiral carbons. This was quite easy and straightforward question. What we have had, the compound was given to us, and we were asked how many chiral centers are present and how many peptide linkages are present. So then we have got the alpha carbon of the amino acid forming bond with the NH2 group of another amino acid. We are calling this as the peptide bond. So here we can see there are 2 peptide bonds and there are 2 chiral carbons present. We'll see. This compound which was given to us was alanine phenylalanine glycine. So the 2 carbons which we are seeing are marked as red color are going to be the chiral carbon, and the 2 bonds which we have shown in the blue dotted square, that is going to be the peptide linkage. Basically, that's the amide bond which is formed by the alpha carbon of the amino acid and the alpha nitrogen of the other amino acid. There can be sometimes different kind of the another NH2 group which is not present on alpha carbon, or another carboxylic acid which is not present on the alpha carbon. They can also sometimes be engaging in the bond formation. Those we are not calling as the peptide bonds. That's the difference between a normal or regular peptide bond versus the amide. Regular amide bond versus peptide bond, that's the difference. Okay, that was quite easy question. Moving on to next question. We are being asked, out of the hydrogens which are present as OH groups, which hydrogen is going to be the most acidic one. So what is going to be the way of, they basically had asked us what is going to have the lowest pKa value. So first of all, when we say lowest pKa value, what does it imply, and then how we compare these 4 different groups. So answer for this is third one. We'll see in a moment how that is happening. The idea is, when we say lowest pKa value, we basically mean to say highest Ka value. And when we have highest Ka value, this compound is going to be most acidic. So now, which hydrogen is going to be most acidic? The answer would be the one where you have got the conjugate base most stabilized, and that most stabilization will be coming from the negative charge of the oxygen atom. So out of these 4 different kind of hydrogens which we are having, in whichever case we see that negative charge on oxygen is most stabilized, that is going to be the most acidic hydrogen, that is going to have the lowest pKa value. Let's have a look. So here we have got the 2 oxygens which were named as 1 and 2. They do not have any charge delocalization because there is no any conjugation situation possible. Out of the hydrogen number 3 and 4, what we have been given, if you go for the position number 4, this is position number 4, this is position number 3. If you got position number 4, This negative charge can be delocalized from here over to this position only. Nowhere else it can go. So this oxygen's negative charge can be delocalized over here. Here only negative charges can be present. So oxygen is sharing its negative charge with the carbon. Carbon, because having less electronegativity, cannot stabilize that negative charge very easily. That's not very much favored. Thinking about oxygen number 3. If there is a negative charge present over here, this negative charge will be going in resonance like this onto this carbon, and then that can be going on to the another carbon. This negative charge is being shared by 3 atoms. We can see here. So when this negative charge is being shared over 3 atoms, out of those 3 atoms, 2 are the oxygen atom. So this is the resonance hybrid where negative charge is present over here, negative charge is present over here, and small delta negative charge is present here as well. This structure is going to be, this negative charge on oxygen is going to be most stabilized. So that is what we are saying is going to be the most acidic hydrogen, and that's going to give us the least pKa value for the given molecule. Like that hydrogen is going to have the least pKa value. That compound was ascorbic acid or vitamin C. Moving on, question number 8 we are having. This question is based on Tollens test and iodoform test. A very much popular question and very straightforward answer. The answer, the question they had asked is, which of the following compound is going to give positive silver mirror test? This is giving positive, and yellow precipitated on the treatment with iodine and sodium. So basically our compound what we have been given is giving both the test positive, silver mirror test as well as iodoform test. So what were the conditions where the silver mirror test and iodoform test are given positive? We need to just check once. Silver mirror test is given by many of the compounds, and among those we have got aldehydes, alpha hydroxy ketones, acetal, phenyl-hydroxylamine, and formic acid. Some other compounds can also be there in certain cases. Also, when we say iodoform test, that's yellow precipitated with this iodine in image, those are given by compounds which are methyl ketones or any other compound which can be converting into methyl ketone, like ethyl alcohol we can have, and other such compounds which can be giving such situation. Sometimes they can be giving us the derivative of, say, methyl ketones, 1 hydrogen is being replaced, 2 hydrogens from methyl ketones are replaced, or 3 hydrogens from methyl ketones are replaced. These are some of the examples where we can be having iodoform test positive. We can have the possible iodoform test given. So what we can think about these compounds which have been given, let us see. The first compound was that 2-hydroxy-2,3-dimethyl cyclopentanone. This compound, what possibility we see? Silver mirror test will be given or not, iodoform test will be given or not. We hardly see a possibility in any of these cases. Alpha hydroxy ketone, because it is present, so there exists a possibility of the silver mirror test, but no other possibility we can possibly see. And actually the breaking of that carbon-carbon bond in the alpha hydroxy ketone, that should be open chain compound where the conversion into the oxidation and conversion into corresponding carboxylic acid could be possible. Here it is going to be very much difficult because there is no such activation of that alpha hydrogen which is present in the benzoin molecule. We have seen that happening. So then alpha hydroxy ketones we have seen. Mostly these are the cases of the terminal compounds. One example which we have seen was benzoin where this was happening. Otherwise, usually this is not happening. Silver test is not given positive by the internal these alpha hydroxy ketones or cyclic alpha hydroxy ketones. Next compound was heptanedione. So in heptanedione, this group is methyl ketone over here on the right. This can be giving us positive iodoform test, but the possibility of that silver mirror test, the Tollens test, is non-existent here. The next molecule was 2,3-dimethyl-3-oxopentanol. Here we have got the aldehyde group present here. That's going to give us the Tollens test, but the Methyl ketone is missing, so we cannot have the iodoform test possible here. Last molecule we are having here, we have got both the possibilities. We have got the aldehyde group present, that's going to give you cellular mirror test, and there is one methyl ketone present, that's going to give us iodoform test. So here is the result, and where both things are positive, that was our answer. So we were asked the compound which is given positive Tollens test and positive iodoform test. That's the case. Here both tests are going to be negative. Here iodoform is positive. Here the iodoform is negative. So that is the case. We have got the correct answer as the last option. The next question in this section, the last question basically of organic in the section 1, it was about the which of the following this was basically based on the preparation of the alcohols from the carbonyl compounds. We are using organometallic compounds or hydride donors, and we are trying to synthesize this compound what has been given to us, 1-phenyl 2-butanol. So how this compound can be synthesized, we have been asked. All these methods are there. There's just one method there which does not lead to this given product. So we have to find the incorrect option basically. That was the area. So see, these compounds which we have been given, the first pair of compound is this, that is phenyl acetaldehyde and ethyl magnesium bromide. That's the second option. Compound number, like the option number B, this was from option number A, this is from option number B. Then here we have compounds from option number C, and here we have compounds from option number D. Now we had to see in which case this is happening. The correct answer over here is, so A is giving, C is giving, D is giving. The only option which is not giving was B, this compound. B is not going to give this compound, that's going to give you something else. Let's have a look. So when we have got the option number A, these things are reacting, we'll be getting this ethyl group attacking onto that carbonyl group, we'll be getting this product formed. Basically this is the ethyl group's new carbon-carbon bond formation is taking place here. That is the new carbon-carbon bond formation taking place over here, and we are getting this product formed. That was the desired product what we wanted. 1-phenyl butane 2-ol. And the second option, when we are reacting these two compounds, when phenyl group is reacting, then this is the new bond formation taking place. This is a product what is being formed. This is 1-phenyl butane 1-ol. We don't want 1-2-ol, we wanted 1-2-ol. So that's not going to be the correct choice to prepare that compound, and that is what will be the correct option basically. This compound, we are reacting this benzyl magnesium bromide with this propanol. So here this is the new carbon-carbon bond formation taking place, and this is going to give you propane 2-ol, because here from we'll be studying numbering. That's your carbon number 1, sorry, that's going to be your carbon number 1, carbon number 2, carbon number 3, carbon number 4. Here it is going to be carbon number 1, 2, 3, 4. That's how there was the difference in the C and B and A options. Option number D, we are using some hydride donor along with some carbonyl compound. So in sodium borate, the hydride is going to reduce the aldehydes and ketones we learned. So that is going to give you, here there is no carbon-carbon bond formation taking place, there's just hydrogen is coming over here. So that carbon-hydrogen bond is basically appearing here. This is the carbon-hydrogen bond that has been formed, and we are getting the same compound we can see as we have been seeing earlier. That is your carbon number 1, carbon number 2, carbon number 3, carbon number 4. So 1-phenyl butane 2-ol is being found here once again. So this only option which is not going to give us the butane 2-ol, 1-phenyl butane 2-ol, was this option number B. That was the last question in our section 1. Now we'll be taking the questions from section number 2, where we have got one or more than one correct options. The first question over here we have been given is about the oxidative ozonolysis of different alkenes or possibly alkynes. The products are given and the reaction sequence. There is a pair of isomers possible for the given molecular formula. Molecular formula given was C5H8. And firstly, we are going to hydrogenated to form C5H10, which tells us that there is only one double bond which is being reduced. Both the double bonds are not being reduced. And then we are doing ozonolysis followed by oxidative workup, which tells us this is oxidative ozonolysis. So how we are going to decide the product upon this oxidative ozonolysis? We need to see the options which were given. I have drawn the structures. So we have got two options. We have got two isomers, isomer number 1, isomer number 2. When we are doing the reduction, then only one pi bond is being reduced. That's what we know. If there is only one pi bond being reduced, that means either this is not a triple bond or there can be any other possibility. So that possibility hardly exists. So basically we can rule out the possibility of the triple bond, and we can think of this compound must be, so this compound may be just any of the alkene. And basically because the degree of unsaturation we can see from here, degree of unsaturation we can find, and basis on that we can take a decision. So degree of unsaturation is 2 only. So if there is 2 degree of unsaturation, because see, degree of unsaturation used to be one good thing to identify how we can go ahead. So we understand degree of unsaturation used to be Cn H2n plus 2. What happened? Cn H2n plus 2, that's the number of hydrogen, and we are going to do minus Cn and CXHY, we can say CNHY better be said. So same number of carbons are there, so difference in the hydrogen over here is going to be, so C5 is going to give you hydrogen as 12 minus C5H8, that's going to be difference of 8 hydrogen atoms. So we do this divided by 2 basically. So 1 by 2 divided by, so this was 4 hydrogens. This is going to be degree of hydrogen, degree of unsaturation is 2. But first option we can rule out because this is going to have both the double bonds reduced. So option number B, C and D we need to see how this is happening, and that for that we have been given the next step, that if you are doing the oxidative ozonolysis, then what is happening. Iso number 1 is giving you this thing, and we can read out from this is going to be a dicarboxylic acid. This is going to be COOH, COOH. Like here there can be some different number of carbons possible in between. And second isomer, they are saying this upon oxidative ozonolysis is giving you just 3 oxygen. So that means this is going to be something where there is going to be one C double bond O and there is another C double bond OH. So this possibility we need to see, so we can identify which alkene will be working and which alkene might not be working for this combination. So correct options for this were B and C. Let's have a look. So when we do oxidative ozonolysis, basically when we start with this alkyne, then if this kind of alkyne is there, we get this product. If you have got C triple bond is C and one side is hydrogen, one side is alkyl, so we get 2 acids, RCOOH and HCOOH. But if you start with this alkene, then if you have got both the alkyl groups, you get ketone formed. If you have got one hydrogen, you get the carboxylic acid. If you have got both the hydrogens on double bond, you get the formic acid. Using this information, we will see how these different products are going to react. So this is the option number A. Here our compound is being split into 2. So this option is not going to work because this bond will be broken completely from here and we'll be getting our molecule split into 2 parts. So here we'll be having 1, 2, 3, 4 carbons only left, while our compound was having the formula as C5 upon oxidative ozonolysis C5H8O4. This is not going to work at all. Then we have got option number B. In option number B, we have got this cyclopentene and 1-methyl cyclobutane. So in this case, you can see here this carbon is having two alkyl groups, alkyl group here, so that is going to convert into ketone. And the other side, you have got here one hydrogen present, so that's going to converting into carboxylic acid. Here you have got both the hydrogens present, so you are getting both the things as the carboxylic acid, as simple as that. So option number B is one of the correct options. Let us see option number C and D as well. Option number C was given us like this. So we have got here hydrogen, here we have hydrogen, here we have hydrogen. These things are converting into carboxylic acid, carboxylic acid, carboxylic acid. The other case, here you have got two alkyl groups. So that alkyl group is going to convert into carbonyl. So option number C is also going to work. What about option number D? See, here these two carbonyl groups are not having any hydrogens present, so there are going to be two carbonyl groups. So this is going to have the formula not as O3 or O4. That is not going to work. The last option also, we can see there was hydrogen, so this is going to be working fine. This is also ruled out. That is how we can find which of the compound can be giving the desired products. Okay. The next question we are going to have is about the formation of hydrate. Here we are given some compounds and we are being asked in which case the stable hydrate will be formed. If we have learned the aldehyde and ketones, we have learned that geminal diols are actually not stabilized in most of the cases, but then there were few cases for some different reasons. So that is what we learned, that the formation of diol, geminal diol, is usually unfavorable for whatsoever reasons. But then there are some certain cases where one case was the hydrogen bonding, and another case can be very high positive charge on carbonyl group. When that situation arises, this can be made favorable. So we need to see in our given example where this favorable hydrate formation can be there. This first compound upon hydration gives what we call as anhydrin, and this next compound, this is hexafluoroacetone basically, that is also going to give extensive hydrogen bonding. So these are going to be the correct options. See, the first case we have got this compound, and basically this carbonyl group is going to have quite high positive charge. Because of this carbonyl, there will be strong electron withdrawing groups. So there can be relatively quite high delta positive charge onto this carbonyl carbon which is present in between. And when we are doing addition of water onto it, then we are getting this kind of hydrate possible. There should have been oxygen over there, hydrogen over here, oxygen over here, hydrogen over here. So when this kind of hydrate formation is going to take place, this intramolecular hydrogen bonding in the product is going to stabilize this kind of compound. So this is going to shift this equilibrium way in the forward direction. So this compound is going to give us stable hydrate formation possible. But in the second compound, cyclopentane known, there is nothing which can be stabilizing these two OH groups, and that is going to give you this equilibrium tending in the backward direction rather than going in the forward direction. Here there is going to be disfavorable, unfavorable change for the diol formation or hydrate formation. This case is we have got the strong electron withdrawing CF3 group present. Here also strong electron withdrawing CF3 groups present. Very strong electron withdrawing group is present. So this attack of water molecule is going to be very much favorable over here. And if that is happening, this kind of product, what will be formed, there is again intramolecular hydrogen bonding possible, and that's going to be fluorine hydrogen bonding. That's again going to be quite stabilizing effect, and here also this equilibrium is going to be shifting in the very much in the forward direction. So that's going to be one of the options, one of the correct answers. And here we have got dibenzophenone basically we are having. Here we are having, because there is a resonance stabilization. Here also there is a resonance stabilization. There is a too small delta positive charge for this water molecule to possibly attack. This cannot be attacking. This kind of equilibrium is favored, not favored at all. This is just remaining in the backward direction itself. So the option to this, the answer to this question was option number A and option number C that we have seen in the beginning. Second last question we are having about the optical isomerism. We are given this compound and we are being asked this given representation X is going to be same as A, B, C, D. Which of these options basically represent the same thing we are being asked? So what we do? We have two possibilities. Number one, we can write their RS configurations for compound number X and every one of the A, B, C, and D. That can be giving us an idea. Or if RS is confusing, it's time taking, then we can directly relate the relative positions of the alkyl or hydroxy or other groups, and we can see how many interchanges can be possible for this compound to generate into the new structure, and that can be giving us the correct answer. So I am sticking with this RS. This compound was written as R because hydrogen is oriented towards us, viewer, and priority number 1, priority number 2, priority number 3. This looks to be anti-clockwise like that, but hydrogen is towards us. So this is going to be named as R. So now if we have any other group present, any other molecule of the ABCD which is coming as R, this is going to be the identical molecule. So the very first molecule is going to be R-phenyl. Again, you can see this is priority number 1, priority number 2, priority number 3. This is rotating anti-clockwise with this hydrogen towards us. That's going to be R. So this is going to be identical. This is going to be one of the answers. Next option was about, and see here basically these two compounds we can also correlate with these relative positions. Like if you see what we have changed. We have changed the relative positions of methyl versus phenyl. Methyl was top, phenyl was at the bottom. Here we have interchanged their position. That was the first interchange. Also you see OH over here was onto the left, H was onto the right. We have interchanged those also. So we can say this to this we have done two interchanges. We understand when we are doing even number of interchanges possible for the same given carbon, same stereocenter, then its stereochemistry remains unchanged. Either of the way we can go ahead with. This compound is going to be S because hydrogen is already away from observer. Priority number 1, priority number 2, priority number 3. This is going to be anti-clockwise. This is going to be S only. This is not going to be the same molecule. This is going to be something different. Here we can possibly see with respect to the starting compound, like here to here we have done just one interchange. What interchange we have done? We have not changed the position of OH, we have not changed the position of methyl, we have interchanged just these two positions. Only one interchange being done, that means we'll be ending up into enantiomer. So the compound number X which was given to us versus compound given on option number B, they are going to be enantiomers. Okay, this was compound number C. Next, in the compound number C, we can see this is going to be basically hydrogen is already away from observer. So priority number 1, priority number 2, priority number 3. This is directly moving in clockwise direction. That's going to be R. That's going to be the correct option. And the last option, option number D, we have got here the hydrogen already away from observer. So priority number 1, priority number 2, priority number 3. This is going to be anti-clockwise. That's going to be written as S. This is not going to be the correct answer. So this is the locating the different groups onto chiral center, and like we can say how many interchanges were being done while doing so. That can be giving us an idea which of these two compounds are same and which of these two compounds might be different. Now we are taking up the the last question for the day, and here we are being given some molecule called beta carotene, and we have here the conjugated system present. So many double bonds are basically present, and we are being asked some facts, the correct statements that can be describing the beta carotene. We need to see whether this is oxidizing, whether this is reacting with oxygen, or this is absorbing red or yellow color, or this is coming in oil phase or not. They have said here that this can be coming in green, red, orange, or yellow, different colorations it can basically be coming. So how our strategy is going to be: number one, we are saying this is reacting with a singlet oxygen, and number two, this is going to be dissolving in the oil phase. Our strategy is, when we have got this conjugated polyenes, when we are saying conjugated polyenes, basically we are saying this double bond, single bond, double bond. This is alternating single double bonds present throughout this chain, like that. Their nature is going to be very much like the standard hydrocarbons, so they are going to be non-polar, and when they are non-polar, they can be soluble in the organic solvents, including oils and fats. Because hydrocarbons are hydrophobic and they are lyophilic. That is what term we could possibly be using. The hydrocarbons are lyophilic. We can say when we are saying hydrocarbons, the first thing what we can say, they are going to be lyophilic, and they were named as hydrophobic as well. So things which are lyophilic, they are hydrophobic usually, and hydrocarbons are falling into that particular category. Also, there are loosely held pi electrons which can be modifying its chemical reactivity or its color, that excitation into the visible resin as well. So option B and D were correct. Here sometimes it seems like we have seen carrot and all, they should be having red to orange or yellow color possible, but this is not absorbing red or yellow color. We'll see why that was happening. So this is basically the molecule beta carotene, and that's the IUPAC name which this molecule has. So many, all of these double bonds except this leftmost and rightmost, all of the double bonds are going to be having stereogenic centers. They are going to be either in E conformation, or they are going to be configuration or R configuration. Okay, so when we say alkenes, basically we remember their name was olefin, which basically which comes from the oil forming from the olefins. So that idea was these compounds are having some affinity with this to be mixed with the organic solvents, or at least with this oil thing, oil compounds like oil, which are having relatively less polarity. And because of their less polarity only, they are going to be soluble in oils and fats. Also, because of the presence of these conjugated double bonds, we can understand they can be very easily oxidized. And if they are being very easily oxidized, this thing is what we can consider as sacrificial oxidation. And when sacrificial oxidation is being used, these compounds are called as antioxidant. They are not oxidizing agent, what was one of the options. They themselves get oxidized, so they should be considered as antioxidant and not the oxidizing agent. Okay. Also, about the color, we understand when we have got the color observed, like beta carotene, the color of carrots and related compounds, when we have seen that color, what is there? That is not actually the color absorbed. That is the color observed. So observed and absorbed, these two colors are having that relationship that they are complementary color to each other. And how we decide complementary color? With that using color wheel. So if we see something where this color observed is orange, red, or yellowish orange, maybe we can think about we are present reddish orange kind of thing. If we are thinking about this color being observed, then what color this compound would be absorbing will be the diurnal color, which we sometimes call as complementary color. So this red orange color will be having complementary color to this one. This will be the color absorbed by this beta carotene. Then this will be color observed. This is color absorbed by beta carotene, and this is the color observed for beta carotene. Okay, so the options what we had seen. The second option, that it reacts with singlet oxygen, that was correct, because this can be forming very easily some of the epoxides. And last option, it comes in oil phase when carrots are cooked in oil medium in water. See, when we have got oil and water, then of course this is going to be mixing with the oil phase, not with the water phase. That is the correct thing. Thanks for watching. We'll be having our discussion in the next session about the inorganic chemistry section A and section B for the same particular paper. Thank you. Bye-bye.